Hello. It's a bit different being back to presenting in person. I feel like last 5 years or so, it's all been Zoom, or like remote. Yeah, it's cool to be in a room with everyone again. So yeah, as Peter was saying, we're going to go through how Canva's working with Tinybird. So I'm going to talk a bit about how it fits in with like our data architecture. So run through the problem we were trying to solve with it, our approach to vendor analysis, because it's quite an important thing to get right. A bit about how we are using Canva and Tinybird at Canva in production. We have been for about a year. It's going really well. And a few learnings about Tinybird, about ClickHouse. This is something that Greg, who's taken the photo, mostly came up with, which is kind of, there's a lot missing. It's
preschool data engineering.
Yeah, so this is kind of just a few arrows. We have quite a few users, fair few. They send us a lot of events, which is good of them. We've got 1,500 or more different types of events. And because we've got a few users, they send us about, at peak, 480,000 events a second or 100 terabytes a day. It's a bit of a challenge. That's why the team I work in now is this analytics backend. So we collect all the events and predominantly send them over to Snowflake, where we've also got a Rube Goldberg machine collecting data from all the databases. As you can imagine, this arrow hides a lot of sins. And so we bring it all into Snowflake, and it predominantly powers machine learning, so training the models, doing BI. And you'll notice this is also missing Apache Spark. It's gone. We got rid of it for good about a year ago, and it's going really well. I want to talk a bit about what we've been terming data applications, because the previous slide covers pretty traditional data use cases, BI, ML, batch, heavy lifting, normal things. When we talk about data applications, I'm really thinking more like components of a service. So it's closely integrated with our product. You want to have a very predictably low latency of the data. So it needs to arrive really quickly. You want to be able to query it really quickly as well. We're talking about milliseconds. Like realistically, you're not going to get a query to start running on Snowflake in less than a few seconds. So it's kind of out. It needs to be very reliable because it's closely integrated with backends directly. And the applications themselves, they could be internal, but they might be user-facing, so directly part of the product. And if you use Canva, you might have seen some of them without realizing. This is an example which on every Canva design, there's a little bar chart in the top right. If you click on it, you see things like total viewers, who were the viewers, things like how did they share the links that are embedded in your design. And this is one of the first examples of the data application in the Canva product, and it's what we based our proof of concepts on, which I'll come back to later. This use case was powered by the first production pattern, which is on the left, which is, it's pretty boring. It's a Java worker that sits there listening to our events. So we've got a stream of data. Java takes them in, processes them, stores it all in DynamoDB, and looks after updating the aggregates when you want to serve it. Do a lookup in Dynamo. Works really well. It's very cheap and low data latency, but it is slow to develop. Like that visualization took a team of engineers about 6 months to get going, get into production, because it's slow to develop. It's very hard to iterate on. Just a quick show of hands, like who here has worked on a data project where the requirements never changed and you never had to update your data model and everything was locked in? Like, you need to be able to iterate on these things. The second pattern that powers a few other things is kind of you load the data in Snowflake, crunch the numbers there, ingest into a backend where you need to cache it because you can't get the backend talking directly to Snowflake. And this works well because you're able to reuse the data modeling approach you have for all your BI and your ML modeling. And that makes some people very happy, but the data latency is typically high. and it's expensive. Because not only are you doing stuff in Snowflake, you're also pulling everything into RDS and DynamoDB. We did a production migration, well, no, a new production use case the other day, and worked out that the whole thing end to end was 10 times cheaper than just the data caching. So like it really adds up. And then quite long query run times as well. So naturally what we did as great engineers was set out to build the entire thing from scratch. I implement our own novel data architecture, our new database that we're going to open source in a couple of years. No, we went out and decided to buy something. So vendor selection is really important because we try and do fewer things as well as we can. So we only want to have one vendor that does one thing. So an example is all our backends are just boring Java Spring applications. We don't have freedom to choose whatever language we like. And within that, we choose one Java library that does the thing. You don't have like 3 or 4 competing ones. So we try and have as small a tech surface area as possible. So we really know how things work. That's why we want to make sure that the vendor that we choose, this kind of use case, is going to last a while and it's going to tick a lot of boxes. The boxes were that it's got to be fast to iterate. So we want to reduce the time to market. We don't want to have people spending months developing a simple chart. It's got to be fast to query. So our backends, we're targeting P99 latency of less than 100 milliseconds. And we don't want to burn a whole heap of cache because everyone is trying to reduce expenses. So a very expensive perfect vendor is kind of out of the question. We didn't talk to everyone in the whole world, right? Like I've got to call out that we did go with 5 or 6 people. We ran 5 POCs. We didn't do one with Materialize, for example, which would be a pretty cool option to explore if you're going to do this yourself. And I'm not going to name names of who the people who failed or made it through the POCs that we didn't go with were, but I will say that AWS TimeStream didn't complete the POC. Like we started and it failed, like outright failure. It was just like really expensive as well. But we assessed them and said cost, performance, time to implement. But there's some soft factors as well, because when you pick a vendor, you're going to be working with them for a few years. So when you do a POC, you should do things like raise a support ticket. And if when you raise the support ticket, you don't really like the experience, that's something to consider because it all adds up. And as Peter spoiled right at the start, the Tinybird one, this is a simple illustration of why. So the red lines are 100 milliseconds. Here are the other vendors. Tinybird was the fastest. But also, like this one, that took me about 2 months, whereas I did the whole thing end-to-end in Tinybird in about a week after picking up the tool for the first time. It's really good. What is it? Hosted ClickHouse. It's got a few APIs on top that help you do things like set up your data processing, like export everything. And they've got a big focus on developer experience and tooling. So they've got pretty nice APIs for how you do deployments and monitoring. They've got this CLI that interacts with those APIs, pretty nice web UI to do your monitoring of the projects and see how everything's fitting together. And there's a sandbox environment, so you can kind of query your data, make sure your ClickHouse SQL works. Pretty similar to like the Snowflake web console in many ways. And similar to dbt, they've got a declarative file format for how you model the data and how you store everything. And so it means you can check in your data project to source control. Some core concepts, which some of them are shared with ClickHouse, some of them are not. They have data sources. Data sources are basically tables. Like any other database in the world, we call them tables. They're called data sources. Kind of an overloaded term, but that's how it is. You have pipes. You have a SQL query in a pipe. It subscribes to changes to a data source, writes to a different data source. So it's kind of like a SQL Lambda. And then you have endpoints, which are SQL queries they're exposed as HTTP endpoints with parameters, which is how you get the data out. So going back to our example use case, I'm going to walk through example Tinybird code to show like how we solve this, and you can see it's pretty simple. This is how you define a data source. So you're saying you've got a design which is in the primary key, time is there as well. And something that's pretty neat for OLAP engines, you can store a partial aggregate. So instead of storing all of the IDs of all the visitors who viewed a design, or instead of storing a count, which like is really hard to maintain, you store the state of the aggregation. So like a hash set that's stored in the database, which means you get to like aggregate by different time periods, for example, but you only store everything once. Like other databases have got it, is like there's a wide range of these functions available in ClickHouse doing things. I used quantiles of query, for example, so you can store like runtimes in different P99s. This was the pipe. So it's just selecting events. So it's subscribing to a data source called events, applying a few where clauses. So it's pretty standard SQL, apart from some things like the unique state. That's how you build the aggregate. And you're saying that it's writing back to that views over time data source we had in the previous slide. Then it all gets exposed in an endpoint. So you get to do basically a stored procedure with parameter injection over a web endpoint. And then getting the data out, you don't have to worry about JDBC drivers because it's just a get over HTTP with parameters. So it's quite powerful and lets you integrate really neatly with like any language because anyone can do a get. So I'm going to have a quick overview of how we've been using it for about a year now. We've got quite a few use cases in production. It's a bit, so we've got like the same analytics backend that we had before, but now you have any service subscribes to our backend, subscribes to the events, pulls the events that they like. Instead of importing all of the application state into the data warehouse to integrate with the events, the backend actually has direct access to that. So it can query it or it can call a different backend to get more information. You don't have to worry about replicating everything. We send data over to Tinybird that does aggregations. And then when a user sends in a request, the service backend calls Tinybird and gets it back. So this is like, it's now become 100% service team problem. Like, we don't have to worry so much about a data mesh and data contracts because it's all owned by the team that looks after the problem. And because it's all owned by that team, they maintain it. It's all the backend engineers. We're not worrying about hiring in a bunch of specialists because, you know, everyone in a team should know how to use all of the databases and all of the tools that are in that team instead of sending it off to another part of the organization to implement account distinct. A couple of examples of things that are live at the moment. Brand Report is like an admin tool for enterprise users. Imagine you've got thousands of seats in Canva. You want to see how your team is using it. You get live numbers on that. So you can see what the templates are in use. You can see how people are using different features. Another one is the creator dashboard. So we have a community of creators who upload elements, templates, videos, audio, and now they're getting live numbers on how all of those assets are being used in the marketplace, which wasn't possible before. And the brand report was possible, but that was powered by the data warehouse, and the data was refreshed once a month. And it normally took a little while to do the refresh. So the page was basically not used, but now it's much more useful. We also have an internal use case, which is monitoring rollouts, something we're still working on. So Canva rolls out all the time, sometimes quite high-profile things, and we want to make sure that our engineers are really confident in what they're deploying. So we give them kind of data that previously would have been a couple of days late in real time on a dashboard for their deployment. We learned quite a bit over the last year, and this isn't like an exhaustive list, but there's some interesting things. So egress costs money. We want to spend less money, so we want to reduce the amount of data that we send out. So we kind of strip out all the columns which aren't actually used in an aggregation. Like we have this massive context object, just a lot of information which is only useful for some aggregations. Just get rid of them. Get rid of all the rows you don't need. And then we used AWS Private Link, which I hadn't used before. It does have a cost to set it up, but because of the amount of data that we're sending to a different VPC, instead of it going over the public internet, it uses kind of a direct connection, like a private DNS record, to go from our services to their load balancer. And we're saving about 100K a year just by turning on one AWS service. Cursor dimensionality stuff is pretty common with any database. Like the more columns and the higher the cardinality within those columns, you need to read more and more rows to answer every query. So as you want to go for like one particular row, if it's all indexed, that's fine. It's just one row read. But if you wanted to read something that's like every blue column here, you suddenly have to start like loading and reading a lot of rows. And this isn't something that columnar storage escapes, because you've still got to look at the row to decide if it fits the where clause. So we had a few tricks to work around it. Every dimension adds cost. So if somebody says, oh, can I put this dimension in your database? If it's like one person and they're not really going to use it, just say no. If you have got a lot of dimensions, try and use them all. Because if people are saying to you, oh, this is super important to me, just make sure they use it all the time then. And also, we try to reduce the dimensionality, the cardinality of the dimension. So an example would be the country. There are a lot. Most people and most dashboards only look at like 10. So maybe just only show those 10 and put other for everyone else. Another good example is the operating system that you get from a user agent. So Darwin, for example, the Darwin operating system name includes the build number and the time that the kernel was compiled. Whereas pretty much everyone, unless you're a data analyst working on Darwin, only cares about the word Darwin. So you just cut out everything else. It's a new database to us. Hadn't used ClickHouse before, but it's, while there's some like very different things, it's pretty standard SQL. One thing, like with every stream processor, joining is something you should avoid. Like, don't cross the streams. If you have to, there are some tricks we've learned. So a limitation with Tinybird is if you've got like a left outer join, the pipe that drives it is actually only triggered by new rows coming in on the left side. So we learned that we had to model a left outer join as both a left and a right, and store the data set that we're joining on in like a really efficiently indexed data source, just to avoid going back to the source data every time. But if you can not do a streaming join and instead do a batch job, then you could use a cron job and run a query like every minute. And it's kind of sad because we're not doing streaming anymore, and streaming is really fun, but it's so much cheaper. Indexing, there were two main types of indexes in ClickHouse important to know about. So partition keys is like reducing the files used in a query. So time broken down to like the month or the week or the day is a good candidate. You want to make sure that writes only touch one partition at a time, and ideally reads as well. Whereas the sorting key controls lookups. It's like, which file should I put these rows in? And when you're answering a query, is like, which file should I be looking up in? And we found that the ordering in the sorting key is super important. We go from the lowest cardinality to the highest cardinality, just like the cursor dimensionality example I had earlier. It really helps like splitting things up. That's pretty much it. So in about a minute, I'm going to stop talking and ask you if you've got any questions. I'm happy to answer anything within reason. We are hiring. So careers.canva.com. You won't find any data engineer jobs because we got rid of the term data engineer. There's analytics engineer and backend engineer, machine learning engineer instead. Or you can email me, guy.n@canva.com. Thank you.